Okay, so we were trying to find the height that a geosynchronous satellite would need to be placed above the surface of the Earth. Remember, geo means Earth, synchronous means in sync with, staying above the same point at all times, which means the period of this satellite has to be 24 hours. So whenever you see the word geosynchronous, it's telling you two givens. It's telling you the period of the satellite, and it's telling you the central body is the Earth. So rearranging Newton's version of Kepler's third law for the radius of orbit, we get g, mass of the Earth, t squared over 4 pi squared, so 6.673 to the negative 11 Newton meters squared per kilogram squared. Mass of the Earth is 5.98 to the 24th kilograms. The period is 24 hours, which of course you have to change into seconds, so multiply by 3,600 seconds per hour, and then don't forget to square it, divided by 4 pi squared, which you, when you're typing in your calculator, need to put in brackets. What you're going to get out is going to be r cubed. And if you've typed it in correctly, which is usually the challenge in this unit, you get 7.545535 times 10 to the 22 meters cubed, and now you need to take the cube root. And when you do, you get, put it in scientific notation, 4.22568 times 10 to the 7th meters. So that's its radius of orbit, but we wanted its height. So we know that the radius of orbit is equal to the radius of the Earth plus the height. So to find the height, it's going to be the r of the satellite we just found minus the radius of the Earth. So 4.22568 times 10 to the 7th meters, radius of the Earth. You can look it up if you don't have it in your head already. 6.38 to the 6th meters. It's on page 955 in your textbook if you're looking it up. And when you do this, minus 6.38 to the 6th, you get 3.58768 times 10 to the 7th meters. Now, when we did the one that was going around 85 minutes, it was 50,000, or 5 to the 4th. This is to the 7th. So it is much, much further away. And that makes sense, right? If it's good, this one was 50,000 and it only took 85 minutes to go around. We want this one to take 24 hours. So it should make sense that it's going to need to be further out. Okay, just a couple of other little notes. There are a few, and Newton could figure them out way back when, a few potential problems with satellites. Okay, and some of the potential problems are human-made in the sense of if we don't get them in the right spot. So one of the issues that can cost millions of dollars is if you don't get it high enough up. If it's too low in the atmosphere, it's going to hit air resistance. There's going to be frictional drag on it. And what the frictional drag is going to do is it's going to slow it down. And remember, it's in that balance of Fg is equal to mv squared over r. But if it loses speed to friction, then Fg is going to win. And it's going to pull it in. And so what will happen will be then it will spiral in to the Earth. And that's not a good thing. There's a few $1 million gone. Another issue would be if when you got it up there, if you gave it too high of a launching speed. Actually, maybe it's as you're launching it from the Earth. Okay, so as you're launching it from the Earth, if you give it too high of a launching speed, it might not slow down and stop at exact height that you need, right? It might be too high up. And if it goes too high up, then it's going to fall into an elliptical orbit instead of a circular one. And it's not good to have a satellite that's not the same distance above the Earth at all times. It becomes a useless satellite known as a rogue satellite. And we have a number of rogue satellites that are orbiting the Earth right now. that, at the launch did not go well. So if you give it, if you give it a slightly too high launching speed, if you give it a really too high launching speed, then it's just going to keep going, and now it's a satellite on its way to another planet to orbit there. Okay, if it's too high of a launching speed, then it's escaped the Earth's gravitational pull altogether. I don't know if this one's ever happened, but I can tell you there were a ton of rogue satellites going around our Earth. Some of them have eventually, got pulled down and burned up in the atmosphere, and some of them are still up there. When we first started putting satellites up, it wasn't regulated all that much, but it didn't take very long before people realized, wait, we have to put some regulations here, because otherwise we'll have 20,000 satellites up there and they'll just get in each other's way. So now it's more regulated. But there are a lot of satellites orbiting our Earth. Some are good and some are not. It was hoped when we put the Canadarm up that maybe we could use the Canadarm to grab some of those rogue satellites and either pull them in or adjust them to get them back on a good orbit. All right, so have some more questions for you because you need more practice. So it's a sheet, universal gravitational questions. I'd like you to do the first 5 for today. And the second sheet is a chart. Okay, and I just want to talk about the chart for a minute. So the top of the chart has all the planets, their radius, their radii, which is from the center of the planet to their outer edge, and then their radii of orbit, which is the center of the planet to the sun, and then their period of revolution, how long it takes them to go around. The lower chart are satellites of the planets, in other words, some moons. Okay, now when you look at this lower chart, be careful of 2 things. One, the radii of orbit are in kilometers, so you need to switch them to meters when you go to use them. And the periods are not given to you nicely. They're given to you in days, hours, and minutes. So you would need to switch the days to hours, add the others, like this, switch your 24 days to hours, then add your other 7 hours onto that, and then switch those hours to minutes and add your other 43 minutes onto that, and then switch it all to seconds to use in the equation. These will come in handy when you need to find like a height or a radius of orbit or a period, and you don't have the mass of the central object. And there are a few questions like number 5 when I tell you you cannot use the mass of the central object because I want you to find it. Okay, and so then you would use these satellites to help you. You would use that equation, r cubed over t squared, this guy, right? So you'd have the satellite, and then you'd have a moon going around the same planet, okay? And you could find the r or the t, all right? So 1 to 5 on that sheet, please.